Good morning. Today we're going to talk about Math 101. We're going to start with Chapter 5 today. Chapter 5 is entitled Systems of Linear Equations. I'll just simplify it a bit. I'll call it Systems of Equations. All right, we're going to begin with Section 5.2. And 5.2 talks about solving systems by a substitution. Two main methods we'll deal with in this chapter. Substitution and the addition method. We'll talk about the addition method later. Today we're going to talk about the substitution method. Substitution. Okay, let's look at example 1. Dive right into the text. Page 309. Please look along in the text if you like. All right, we'll say solve the following system. Now, by a system of equations, we really mean solving, at least in the beginning, solving two equations simultaneously. Some books call these simultaneous solutions or simultaneous equations, depending on what book you read. Y equals 11. All right, we're given this system. Really, it's two equations that we're asked to solve simultaneously. In other words, find an XY pair that work in both equations. All right, in the substitution method, what we do is solve for, pick one equation and solve for one variable in terms of the other, and then substitute the resulting expression into the other equation. Let me show you what I mean. This first equation looks like I can solve for x pretty easily. If I solve for x, I'll get x equals, let's see, minus 3y plus 18, just subtracting 3y from both sides. Then I'll take that resulting expression for x and substitute it in for x in the other equation. All right, that will result in one equation with one unknown variable that I should be able to solve pretty easily. All right, let me go ahead and make that substitution. Into the second equation, I get 2 times minus 3y plus 18 plus y equals 11. Substituting minus 3y plus 18 for x in that second equation. All right, the result is one equation with one unknown, which I hopefully can solve pretty easily. All right, I'll multiply through by 2 here. Breaking out that y variable from parentheses, I get minus 6y plus 36 plus y equals 11. And of course, now I can combine like terms. I would probably add y to minus 6y first. I'll get minus 5y plus 36 equals 11. Then, of course, subtracting 36 from both sides, I'll get minus 5y equals minus 25 on the right. I'll now divide both sides by negative 5. The minus 5's cancel on the left. I get y equals a negative over a negative is a positive, and 25 over 5 is 5. All right, so I've solved for y, so my solution is going to look like this. Well, we know y has to be 5 to solve simultaneously in these two equations. What's x going to be? Well, what I can do is substitute y equals 5 into either of these equations and solve for x. And either one will work. I'm going to pick the first one. Maybe it looks a little easier. X plus 3y equals 18. I'm going to substitute y equals 5 for y and then solve for x. All right? So x plus 3y equals 18. Remember, we're going to plug in y, or 5 for y. X plus 3 times 5 equals 18. Of course, 3 times 5 is 15. So x plus 15 equals 18. And x then equals 3, subtracting 5 from both, or subtracting 15 from both sides. So the simultaneous solution to both of the given equations is 3, 5. X is 3 and y is 5. Right? And we might want to put our answer in ordered pair form. Right? Either one of these answers is fine. Either the ordered pair 3, 5, or the explicit statement x equals 3 and y equals 5. Okay? All right, let's try example 2 in our text. This is example 2 on the bottom of page 309. Please turn there and follow along. We are given another system, 2 equations, which we are asked to solve simultaneously by substitution. Right, so the book instructs us solve by way of the substitution method. And we'll do it similarly. You solve for one variable in terms of the other, and then substitute the resulting expression for that variable in the other equation, resulting in one equation with one variable. All right. If you look at this system, well, this first equation begs to be solved for y, right? If you look, y has no coefficient on it, so I can easily take that first equation, I'll label it equation 1 if you like, 2x plus y equals 3. We can easily solve for y by subtracting 2x from both sides, so y equals minus 2x plus 3. And that expression for y can now be substituted for in the other equation, right? I can plug in this expression for y right here in this second equation. All right, that will result in then substituting 4x plus 2 times that expression for y equals 12. All right, now I'm going to, of course, multiply through here, distribute that 2 factor, minus 4x plus 6 equals 12. All right. If you'll notice then, these cancel out and I'm left with a nonsense statement. 6 equals 12. And if you reduce to a nonsense statement like this, then there are no solutions. And that can happen sometimes. Right? No solutions. There is no XY pair that will solve both of these equations simultaneously. Okay? Example 4 on page 310, right at the bottom. A little bit of a harder example. Again, a system, a 2x2 system, 2 equations with 2 unknowns that I'll want to solve simultaneously. In other words, find the XY pair that solves both equations at the same time. And they ask us to do it by the substitution method. That's a 6 there. Let me clean that up. All right. That's a 6. All right, solve by substitution. All right. In the last 2 examples that we did, we had at least one term that had a coefficient of 1. It which made it easy to solve for. Here we're not so lucky. None of these variables have coefficients of 1, but I do notice in the first equation all these coefficients are multiples of 3. If I divide both sides here by 3, I get a resulting equation that has an x coefficient of 1, does it not? So let me take equation 1, and with a little surgery we should be good to go. I'm going to divide all terms, both sides, by 3. 3x over 3 reduces to x, plus 6y over 3, 3 cross cancels into x twice, x plus 2y equals, and 9 over 3 is 3. And with one more little surgery, subtract 2y from both sides, I will have solved for x in terms of y. All right, so x equals 3 minus 2y using that first equation, solving for x. I'll then take this expression for x, plug it into the other equation. That will result in one equation with one variable. Here we go. Let me take the second equation then. 2 times 3 minus 2y, substituting in, minus 3y equals 6. I'll need to distribute this factor of 2 to break out those terms from parentheses. I get 6 minus 4y minus 3y equals 6. I'll get 6 minus 7y on the left, combining like terms equals 6. All right, so minus 7y equals 0, subtracting 6 from both sides and dividing both sides by negative 7. The minus 7's will cancel out on the left, and 0 over any denominator is 0. So I've got half of my solution there. I know that y has to be 0. All right, if y is 0, I can plug that in to either of the equations above, either the top or the bottom. Let y equal 0 and solve for x. Since this is a simultaneous solution, it doesn't matter which equation you use. I'll pick the first one, 3x plus 6y equals 9. Let me do it over. I'm going to need some more room here. All right. Taking that first equation, 3x plus 6y equals 9. I'm going to plug in y equals 0 here. So 3x plus 6 times 0 equals 9. That's a multiplication there. Well, anything times 0 is 0, so I got 3x equals 9. And dividing both sides by 3, I'll get x equals positive 3. So for both these equations, when x is 3, y is 0, those coordinates will solve both equations simultaneously. And again, you can leave your answers like this with explicit statements for x and y, or if you like, put it in ordered pair fashion in coordinates. X is 3, y is 0. Either way is fine. All right, the next one's a little bit nastier. Let's look at example 5 on page 311. All right, write down the system here. 6x plus 8y equals 3. That's an 8 there. 6x plus 8y equals 3. And the second equation, 3x equals 3y plus 5. All right, well, the idea here is I don't think we're going to be able to stay away from fractions here. That's too bad. Well, we'll just have to deal with it. Sometimes you have to deal with it here. If you look at this system, 2 by 2 system. Well, the second equation can be easily solved for. You can solve for x just dividing both sides by 3. Let me take the second equation. 3x equals 3y plus 5. And I'll divide both sides, all terms, by 3. Now, of course, the bad thing here is 5/3 doesn't reduce. Well, we'll just have to deal with the fraction then. All right. On the left-hand side, I will get x equals. On the right-hand side, the 3's cancel out, and I get x equals y plus 5/3 as an expression solved for x. All right, I again will work this similarly. Take this expression for x and plug it in for x in the other equation. Let me erase that. I'm going to go to equation 1. And sub in that expression. All right, you see multiplying by 6 will get rid of that 5/3 fraction in a moment, so maybe we're not doing too badly here. All right, let me write that out. I'll take 6 times this expression right here, 6 times y plus 5/3 plus 8y equals 3. All right, this gives me one equation with one unknown. I'm going to again multiply through here by 6. 6 times y is 6y plus 6 times 5/3. Well, 3 cross cancels into 6 twice, and 2 times 5 is 10, plus 8y equals 3, multiplying through by the parentheses through by 6 and eliminating the parentheses. All right, I can now combine like terms. 8y plus 6y is 14y plus 10 equals 3. I'll now subtract 10 from both sides. I'll get 14y equals -7. 3 minus 10 is -7, subtracting 10 from both sides. And now dividing both sides by 14, I'll get y equals -7/14, which of course reduces to -1/2. All right, so I'm halfway there. I've got a solution for y. Y equals -1/2, and we'll just have to live with the fraction. All right, what's x? Well, how should I plug in y here? Well, I think if I pick this second equation, well, let's see, the first equation, if I use this first equation, I'm going to be multiplying -1/2 times 8, and I think that fractional will disappear, at least temporarily. Let me erase this work here. Again, now I can pick either equation I want. I'll take this first one. 6x plus 8y equals 3. Plug y equals -1/2 in for y, and then solve for the remaining x variable. Okay. I get 6x on the left plus 8 times -1/2 is -4. All right, so 6x, if I then add 4 to both sides, I get 6x equals 7. And solving then for x, I get x equals 7/6. All right, so the solutions here are 7/6 for x and -1/2 for y. Or if you like to answer in ordered pair notation, 7/6 for x and -1/2 for y. That's not too bad, even with the fractions. All right, I want to do a couple from the homework list. This is on page 313 from the exercise set 5.2. And number 14 we're going to do. It's 2x plus 3y equals 7. Equation 1, and then the second one, 6x minus y equals 1. And again, the book asks us to solve with the substitution method. All right, I'm looking at these two equations, and I think the second equation begs to be solved for y. We can solve for y here pretty easily. I'll take equation 2 aside. I'll say 6x minus y equals 1. Well, I can add y to both sides. So 6x equals 1 plus y. And then if I subtract 1 from both sides, I get 6x minus 1 equals y. I have now solved for y in terms of x, and I can now plug this equation, this expression for y, into the other equation. All right. So let me go ahead and write that out. I'll get 2x plus 3 times 6x minus 1 equals 7, substituting this expression for y in the other equation. I'll perform this multiplication. 2x plus 18x minus 3 equals 7. Let me check that. 3 times 6x is 18x. Minus 3 times 1 is 3. Looks good. I'll get a 20x combining like terms on the left. 20x minus 3 equals 7. I will then add 3 to both sides. 20x equals 10. And then divide both sides by 20. X equals 10/20, which of course simplifies to x equals 1/2. All right, so that's half of our simultaneous solution. All right, if x equals 1/2, and again, you can now plug that 1/2 value into either equation. I'm going to pick the first one because I see a 2 multiplier there. 2 times x is 1/2, we now know, plus 3 times y equals 7. And we can solve for y hopefully pretty easily. The 2's and the 2's cross cancel here. I get 1 plus 3y equals 7. Subtracting 1 from both sides, I get 3y equals 6. And of course, dividing both sides by 3, I get y equals 2. So my simultaneous solution is x equals 1/2 and y equals 2. And again, in ordered pair notation, it would be the point 1/2, 2. All right, last one today. We're going to do number 22 on page 313. Another 2x2 system. 5x minus 2y equals minus 7. And 8 equals y minus 4x. All right, 2 equations with 2 unknowns that we're asked to solve for simultaneously. All right, we'll do it by substitution. Solve by substitution. All right, I think it's pretty clear in the second equation. It's probably best to solve for y here. Here's y with a coefficient of 1. All I need to do is add 4x to both sides in equation 2. And I'll get y solved for very nicely. So take equation 2 aside. I'll get 8 equals y minus 4x. Add 4x to both sides. I'll get 4x plus 8 on the left equals y on the right. I've now got y all alone solved for nicely on the right-hand side. If y equals 4x plus 8, I can then substitute 4x plus 8 for y in the other equation. Okay. That will give me the resulting equation, 5x, hang on a minute, 5x minus 2 times 4x plus 8 equals -7. I'm going to perform this multiplication here. 5x minus 8x minus 16 equals -7. Multiplying this parentheses through by -2. All right, I've got some like terms here. I'll get -3x minus 16 equals -7. If I add 16 to both sides, well, 16 minus 7 is, of course, 9. And if I divide both sides by -3, the -3's cancel on the left, and I'll get x equals 9 over -3, of course, reduces to -3. So I know in our solution that x has to be -3, and now I'll plug in that value of -3 for x again in either equation here and solve for the remaining y variable. All right, I'm going to pick the second equation. 8 equals y minus 4x. X has to be -3 in the solution, so I'll say 8 equals y minus 4 times -3. I can now solve for y. 8 equals y, well, -4 times -3 is +12. And if I subtract 12 from both sides, I then get y equals -4. All right, so y equals -4 when x equals -3. That pair will solve both equations, and I can list my answer in ordered pair form if you wish. All right, this concludes section 5.2, solving equations by substitutions.